Ok, bon. Je commençais. Ok, je suis pas, je suis pas, je suis pas. Moi, je fais toujours les GitHub des gens. Mais bon, moi, c'est cool. Hmm. Bon, je sais pas. Je fais. Bon, pour aujourd'hui, je sais pas trop, mais je veux travailler sur. Ça, c'est question, c'est sur Database AI. Ça, c'est cool. Et c'est prochain. Ok, on va mettre le détail et puis on va commencer. On a déjà cliqué sur les liens. Ok, le but c'est we are not paid to teach class and do not monetize the class anyway. Make all the class material motion track free. If you want to support motion, best way to do is to spread the word about the class. If you recover the motion to other. Ok, motivation as a competence. We know that computers are great motion track data effort to often forget that this apply just as much as to use computers as to. Ok. Bon, je pense que je vais tomber. Voyons voir où est-ce que share. What is share computers? Attends, je lis d'abord tout ça avant de regarder la vidéo, bien je regarde la vidéo. Ah, je sais pas, mais on va juste. Ok.
37, which is an optimal start time for first class. So welcome to the first class of Missing Semester IP 2026. This is a class that we originally ran in 2019, and then we ran it again in 2020, and then we all kind of moved on to other things, but enough people seem to find this class useful, and there are enough things that sort of changed since last time that we decided to run another iteration. That's what we're here for. We're sort of co-lecturing the class together, same as we did back in 2020 and 2019. I'm John.
I'm Manish.
Oh yeah, that's a good idea.
Is this thing on?
Yes.
Oh, yeah. I'm Manish.
And I'm Jose.
All three of us are ex-MIT students who did this class while we were doing our PhD here. We've since sort of moved on to other things. The other things are not particularly relevant, I think, for this class, so we're not going to do a whole what else are we doing. But enough to say that we all took a bunch of classes at MIT, and all of us sort of fell through this pain of all of the things that you're supposed to know in some way, or at least the classes sort of assume that you know, like Git and editors and how to get around on the terminal and what the terminal even is. And we felt like there's sort of a superpower here in that if you know how to use these environments well, then it makes a lot of other things in these classes easier. The problem is no one teaches it to you, hence the name The Missing Semester. And so the goal of this class in all past instantiations and in this one is for us to go over all of those things, or at least as many as we can fit into the time. All the tools, techniques, concepts, ideas that sort of make up the bulk of the behind-the-scenes knowledge. I don't know if you have other things you want to add before we dive into the first topic.
Yeah, just a little bit more on the inspiration for this class. So all three of us, while we were grad students here, TA'd a bunch of classes, and we often found that while in office hours we'd be teaching students topics that were actually not the subject matter for the course we were teaching, but just things like how to use the shell, how to make most effective use of the text editor, and things like that. And so we thought, let's factor out all of those topics and teach a dedicated course on it so we can focus on the course material in office hours.
Yeah, I think some of it is also like repetition. Like there's a lot of things, we think about computers like we can write programs that automate things, but we don't think about the fact that the computer can automate our tasks working with the computer as well. Like you have I don't know, you're running the tests for some lab and you want to run them until they fail because you know that they fail if you stress test them enough. And instead of you pressing like arrow up, enter to run it multiple times, how can you automate this task? And so those kinds of things are things that students don't even know to ask questions about because they don't necessarily know that it's possible. And those are the kinds of things we want to give the insight to in this class.
Yeah, just to add to that, I feel like a bit of it is unknown unknowns. Like you might not know that like a lot of smart programmers have come before you, already like faced these frustrations and already have solved these problems. It's just like, since these solutions are not taught in your compilers class or in your algorithms class, you might not know about them. And I think part of what we're trying to cover here is just giving you awareness of the types of
bunch of different using the email that's on the website. Cool, let's dive into the first topic, which is dramatic effect, the terminal, or more specifically, the shell. What is the shell? Well, computers have a bunch of different interfaces you can use to interact with them, right? We're all familiar with graphical user interfaces, or GUIs. Those are the ones where you move your mouse around and you click things. And those are fine. They work really well if they're well-designed graphical user interfaces. We have other things more recently as well. We have things like agentic interfaces. We have voice interfaces. We have virtual reality, augmented reality type interfaces. Maybe we'll get neural interfaces at some point, right? We have all of these ways to interact with the computer, but the reality is that a lot of those interfaces are sort of specialized. They're specialized to what the author of that interface had in mind when they created the interface. So for a GUI, for example, the only things you can do are the things that are programmed into that program to do. Similarly, it's pretty hard to take two different programs that are doing maybe related tasks and you wish you can combine them, to try and actually combine them is often pretty hard. It requires there to be some custom implementation of like software A from vendor A with software B from vendor B so that those two can interoperate. And sometimes you really just want to drop into sort of one level lower where everything is just, you can write whatever commands you want, you can chain them together however you want, and that is what the shell is. It is the textual interface to the computer. This is the thing that we sort of had from the very beginning. This is what preceded all the GUIs, it preceded all the other interfaces, and it is in a way the sort of core language for interacting with the computer. The shell is really a program on your computer that lets you give inputs commands and prints the outputs of those commands, and that's how you interface with it. The shell runs in the context of a terminal. A terminal you can think of as like the GUI window that is around it. So in this case, you can see that there's sort of a border around this thing. That is my terminal. It doesn't have any UI. Some terminals do, mine does not. And inside of that terminal runs a shell. You can open a terminal on your computer. Most computers these days ship with some kind of terminal with some kind of shell. On Linux, you can usually open this with like Control-Alt-T tends to work on most distros, or you can open your application launcher and just search for terminal. You should probably find something. On Windows, you type the Windows key in R, and then you can type either CMD or PowerShell. Those will open the same terminal but with different shells. And on macOS, command space to open Spotlight, and you search for a terminal, you get a terminal. Now, the terminal you usually don't need to worry too much about. It gives you things like interactions with operating system, things like copy-paste or mouse movement and selection. But apart from that, most of the interesting stuff here is going to happen in the shell. The shell that is most commonly used sort of across the board is the born-again shell, or bash. Bash is what you're going to get on Linux usually when you start a terminal. On macOS, it also used to be bash. These days, it's something called ZSH, or ZSH. This is also now the default on some Linux distributions as well. ZSH is a bash-compatible shell. So things that are valid in bash are usually valid in ZSH, and ZSH has a bunch of other ergonomic improvements and feature improvements that make it easier to interface with. You'll find that there are actually a lot of different shells that are often built for different purposes. And in fact, there are some that, like bash is pretty old and has not seen significant new feature expansion since then. ZSH does have a lot of ergonomics improvements, but there are also shells like fish that are intended to be written by humans on the command line rather than by programs or in programs. And you'll find that if you talk to the instructors, like all of us use different shells for different reasons. And this is also something where you could choose to explore your own shell down the line. But for the initial sort of investigation and for everything we cover in this class, we're going to be focusing on bash and sort of by extension also ZSH. On Windows, you will not get a bash-compatible prompt. You will get either batch, B-A-T-C-H, or you will get PowerShell, the newer version of the shell for Windows. These have similar concepts, so what you find in bash and similar shells, but they are kind of different. Their syntax is kind of different. The way you invoke programs is kind of different. We will not cover those in this class. If you're on Windows, I recommend you install either the Windows Subsystem for Linux, WSL, or you install a Linux virtual machine that lets you get access to a proper shell. PowerShell is also very good, but for very different reasons. But so in this class, we'll focus entirely on bash and its derivatives. Now, why should you care about the shell? Well, it's usually much faster than clicking around. Once you get used to the shell, you can do quite a lot of things with very few keystrokes. Whereas in a GUI, it tends to become more laborious, especially the more complicated your task is. And part of this is because in the shell, you can automate. The shell is essentially a programming language that, the command line, the prompt that you see up here, where I get to type things and they appear, that prompt is essentially the start of a file that I get to write that is a bash program that gets executed. Most of those programs are very simple. They're just start a program of some kind. But you can write fairly complicated expressions here, as we'll get into later. There are a couple of other reasons why the shell is useful. One of them is this ability to combine programs. We'll see that as well. How you can take the output of one program and feed it into another program that does something else, and feed it into a third program that does something else. The shell is very much built for that kind of combinatorial thinking, if you will. Knowing your way around the shell is also useful for interacting with the open source community. You'll find that for almost any open source tool you find, the instructions for building it, installing it, running it are all going to be things that happen in your shell. You'll also increasingly find things like, how do I do this on my computer? And you'll be told to open a terminal and type something in there. And usually it's useful to know roughly what that command does rather than just blindly copy pasting things from Stack Overflow and going, yeah, it's probably fine. Right? So hopefully this gives you a bit more sort of intuition and insight into what those things actually do and which things you should be worried about and which things are not. There's also increasingly use of shell in, and bash in particular, in configuring continuous integrations for projects. You'll find this both in the open source community and also in the closed source community. If you end up taking a job at a company, you'll find that a lot of the configuration for how the software is built behind the scenes, how it is tested, how all of those pipelines flow together is also all done using shell commands. So let's then look into what is the shell. Well, so as I already explained, here we have the prompt. The prompt is the main interface you have to your shell. And it tells you, this sort of start of the shell prompt over here, tells you that my username is John. It tells you that the host name of the machine I'm on is XOS. The colon is the separator, just like the ampersand. And the thing after, the squiggly line, the tilde, is the location I am at in my file system. Tilde is short for my home directory. So currently I'm in my home directory, is what this prompt is telling me. The dollar is telling me that I'm not the root user, I'm not the admin user in this shell. Usually you'll just see dollar here and you don't have to worry too much about it. And then it's just sort of friendly waiting for me to run a command. Now, when you run a command, why does the sound double when I'm standing over here? It's disturbing. Is that still on maybe? No? Weird. Is there a secret microphone? Ah, well, it'll be okay. So on the prompt, you can type commands that you want to be executed. And the simplest kind of command you can type is just the name of a program. So for example, there's a program called date, and perhaps unsurprisingly, when I run the date program, it prints the current date to my terminal. And then I'm dropped back in a prompt where I can now type more things. We can also execute commands with arguments. So arguments here are things that follow the program name in the command. So for example, the echo program is one that will take the arguments we pass to it and print them back out. So for example, if I type hello world here, it prints out hello world. So hello and world here are arguments to the echo program. It's worth spending a few seconds here on what argument parsing is. Argument parsing in bash is that you take the string, the text that the user gave you, and you split it at white space boundaries. And each white space separated word is one argument, and the first argument is the command, the program to execute. Now, there are ways to say that I want an argument that has white space in it. So you can do quoting just like you can in most other programming languages. Now, echo prints all of its arguments, so it's not going to be particularly useful there. But I could, for example, say hello world like this, and it will print the same thing because echo defaults to printing space separated of its arguments, which is the same thing I'm providing here. But for example, if I put more spaces in here, you'll see that now this gets treated as one argument that gets printed as a single thing. If, on the other hand, I typed hello and then a bunch of spaces in world, these are just two arguments to echo. They get separated as two arguments. The white space is ignored. It's just a separator. And then those two arguments are provided to echo, and it prints them back out. Argument parsing is something you're going to run into a lot when you start writing command lines yourself, because sometimes getting the quoting right can be quite annoying. Yeah?
Okay, first of all, why don't the program names have like .java or something? Or like, do they normally have .java, or do they not normally have .java, or like .py or something?
So these programs, I'll get into where we find these programs later and where they're located. A lot of these are pre-compiled programs that are installed on your computer. So they're not source files. They are programs that are built into your computer or that you've installed after the fact.
Okay. And the strings we write afterwards, if you write Java with the public static void main string args, this is the string
Right, so the question here is if you write, like for example, a Java program and you write a sort of static main function and the args argument you get to that function, those are exactly what these arguments turn into. And the same thing for Python. If you want to access the argv thing that you get in Python, that is a list of arguments provided to the program, this is where those arguments come from. You'll find that you end up running into quoting issues here once you start getting more complicated things. Like maybe you have a path that has a single quote in the name of a file. Well, now you need to use double quotes around it, or you need to escape it. And escaping is simply putting a backslash in front of a character. You can do this multiple times to escape multiple characters. And now you see it has the same effect as though I quoted it. But doing this once you have let's say you have a path that includes spaces and also single quotes and also double quotes, and then you might need to get creative with the quoting that you do so that the arguments end up being split in the correct way. You will run into annoyances around this. It takes a little while to get used to, but there are ways to sanely quote any argument to a command in Bash. Semi-sane. Yep.
So backslashes separate the same as white spaces?
No, backslash is an escape character that says don't treat the next character as special. So in the case of argument parsing, backslash space means a literal space. Do not split on this. This is not a word boundary. It is a literal space that's part of an argument. Cool. Now, perhaps the most important command or program you will find to use in, yeah, you had a question?
Oh yeah, I was just going to ask if you could show how escaping works for quotes too.
Yeah, so if I wanted to say, this would not work because it would think that this is one string, and then it would say there's a trailing single quote here that doesn't get terminated. So it just tells me, oh, it drops me back in a continuation prompt, which is the thing you see at the bottom where it's just expecting more input. If I put a single quote here, then it will get confused and all the single quotes are gone. And so what you could do here is either say this, or you could double quote the whole string. And so that way you would end up with the expected output. Now, one of the most useful programs you'll find on here is a program called man, short for manual. The manual allows you to pass in the name of another program, and it explains how to use that program. So for example, if I type man echo, so echo is the argument here to man, I get a manual page. And this says echo displays a line of text. And then it shows me all of the options, all of the arguments that I can pass to echo. And usually some of them will have version information at the bottom. Some of them will also have usage examples. So if I look at the manual page for date, you'll see it prints a date. And it also, oh, this doesn't have that either. If I do bash maybe. So the bash one is pretty extensive. And it has bug reports and authors and files and restricted, like it has a huge manual page that explains all the various things you might want to do in bash. So the man program is one you will find you can use a lot in order to understand more about the commands you have and what things they can do. Usually you can get a short version of the manual page for a program by simply passing --help as an argument. So in this case, when I run date with --help, it prints out the help string for date, which is usually slightly shorter than the man page. Some commands also allow just -h as a similar thing. After man, the most important program to know about is CD for change directory. Change directory allows you to change where you currently are in the file system. In this case, like I am currently in my home directory, and so in my home directory, like there are a bunch of files, but if I wanted to operate somewhere else in the file system, I could change to be in that directory instead. So what does that look like? Well, I type CD for change directory, and then I type a path. So a path, in this case, it's a path that starts with a slash, so that makes it an absolute path. We'll get into other kinds of paths later. So I want to go into the bin directory under the root of my file system. So I want to change directory into there. When I do that, you'll see that my prompt has now changed. It now says I'm in /bin instead of being in /home. I can also CD directly into the root, and so on. Now, you'll find that there are a lot of commands that will operate in the current working directory by default unless you tell it something else. So that's why it's usually useful to know where you are, hence why it's in the prompt, and to potentially change where you are. And it's particularly useful because it allows you to use relative paths. So here I did /bin, but imagine that I have some path that's deep under my home directory. So it's like /home, /john, /dev, /project, /6824, /version1, and it becomes a really long thing for me to type all the time. So instead, I can change directory into the folder that I want to be operating in and then use relative paths. Relative paths are any path that does not start with a slash. And the resolution for a relative path is in the current working directory, look up the first path component. Path component are the slash separated parts of the path. Look up the first one, and then from there traverse using slashes, rather than starting at the root of the file system. So for example, I'm now in slash. I can type cd bin, note the lack of a slash, to say I want to change directory into the bin folder of what inside of the current directory. If I'm now in bin and I try to cd to bin again, it would tell me there's no such directory because it looks for a folder called bin in /bin. If I go back to slash and then try to cd to slash, well, that's fine, that's an absolute path. But there are a couple of other special kind of path components you can use in relative paths. You can use them in absolute paths too, but they're more common in relative paths, which is dot and dot dot. So dot is the current directory. It might seem weird, but I can cd into dot, and it cds me back into the same place I already was. So if I cd into bin and then cd dot, I'm back into /bin. So it's just a way to refer to where you currently are. This can be useful. We'll see some examples of that later. The other special path is dot dot. And dot dot refers to the parent directory of wherever we are. So if I do cd dot dot, I end up in slash. I end up one level up in the file system. If I try dot dot from slash, like the root of my file system is special, where dot dot just goes back into slash. But what I can do is I can chain these. So I can say I want to go into bin, and then I want to go back out, and then I want to go back into bin, and then I want to go into itself, and then into itself again, and then I want to go back to the root, and then back into bin, and I end up in /bin. So you can combine these to create paths that navigate the file system however you see fit. Yep?
What is the use case of this?
What's the use case of this? The use case of this is, imagine you're operating in, I don't know, you're working on a 6824 project. And now you want to move to working on a 6858 project. Well then, instead of typing, okay, I'm in 824, instead of now having to use an absolute path to say, now I want to seed into home John dev 6858, I can just do cd dot dot slash 6858. So go one up and then one down into a different directory. This particular path you probably wouldn't use because this is pretty useless. But you don't have to say the same path again, right? You could easily, because once you've done the dot dot, you are now in the reference point is one level up in the folder hierarchy.
So tilde represents enter.
Yes, so if I do cd tilde, you'll see I end up back in my home directory. Slash is the path's component separator. It is the thing that separates each recursive step of resolving the path. So if I go to cd a/b/d, a/b/c, what that means is change directory into A. After doing that, change into B. After doing that, change into C. So that would go into D, the folder C that's inside the folder B that's inside the folder A. And these paths also work with tilde. So I could do tilde slash dot dot, and I end up in slash home, because it's one directory up from my home directory, which is slash home slash John. There are more efficient ways to navigate the shell as well. So you'll find, for example, in the lecture notes, there's a reference to a tool called zoxide that remembers all the paths you've ever CD'd into, and then gives you a more rapid way to CD into arbitrary of them rather than navigating the whole file system. So there are tools people have built to more efficiently navigate the shell, but this will already get you there pretty quickly. There's one more trick that's useful to know here, which is tab. Tab in Bash gives you autocomplete. And so, for example, if I do cd b and then press tab, well, in this case, B is ambiguous. Oh, that's because I'm in the wrong place. cd b and then press tab. You'll see if I double press tab, it gives me all the possible options. In this case, /bin and /boot are both directories I could go into. But if I do cd bi and then press tab, it auto-completes to bin. And so this is one way to more rapidly navigate through folders, is you just type the first few letters and then type tab. And if those are ambiguous, tab will show you the options. So what kind of things can we execute in the shell? So we've already talked about echo, date, man, and cd. But how do we figure out what else is available to us? And in fact, how does the shell even know when I type date which program to run? Like, where is date on my computer? The reality is that when you type a command with a program name into your shell, what it would actually do is it will take the name of the program and it will look it up in something called path. Path is an environment variable, so it's a variable that's sort of set across my whole shell of variable to value mappings, usually names to strings. And those will describe a bunch of meta information that the shell can make use of, like what user am I, what host is this, what shell is being used, that kind of stuff. And path, and here we can use the echo tool again. If I echo my path, it will list out a sequence of paths. They're colon separated here. And when you try to run a program in your shell, it will walk through these folders one by one, looking for a file by the name of the program. And if it finds it, run it. Otherwise, look in the next one. And we can actually introspect this if I run which date. So which is a program that will walk through the path list and print out the place where it first finds a given program. It will say that the location of my date command is at this path. So when I run date, what actually happens is my shell discovers that path /run/current system /swbin date, and then runs that program, executes that program, and that's what ends up in my terminal. And this is so that we don't have to write the full paths every time. So I could, if I wanted to, take this path and have that be my program name, and that will run just the same. But it's more convenient for the shell to be able to discover them in this way. Which is also just a program, so I can run which, and it tells me that the which program is located in the same folder as date was. This path might be different on your host. It just depends on where software is installed on your particular operating system. Do you have a question?
Okay, so when you type it non-completely, it searches in folders that it searches in the parents of your current directory.
No, it searches in the folders listed in my path.
Oh.
So the path variable is sort of a special variable that's known by my shell, and it will search through these directories in order for the program by the name that I gave.
If you have multiple programs of the same name in more than one folder that's in the path, how does it choose which one to run?
So if a particular program is present in multiple paths in my path, like $path, my shell will execute the first of them that it encounters in the path order. And you can even ask which, with the -a flag, which is for all, I can ask which all the copies I have of echo. And it will say there's only one echo for you. If I try to do something else like Rust C, well, there's also only one. Do I have anything that would be multiple of? SH. You'll see that there are actually two places in my path where SH appears. And it will show all of them. But your shell will normally execute the first one only.
Wait, what's the -a for?
It's an argument to which that makes it print all of the paths rather than just the one it would have selected. And in fact, if I tap man which, you'll see that there's, under options, it says -a or --all, prints all matching executables in path, not just the first. And this also gives us a clue for how we can figure out what all of the programs we have are, right? Is that you could walk through all the directories in your path and then just list the contents of all of them. And that is all of my programs. You might not know what all of them do, but you could do that by looking up the man pages and then explore. So if you really want to go through this process, so in my case, for example, I could take this directory and do ls and this path. ls is another program that is the list program. It lists the contents of a directory. So in this case, I'm telling list, hey, can you go list the contents of that directory? And if I do, it prints out a long list of all the file names that are in there. And these are all programs that I could run on my command line. One thing worth noting here is if I type ls and don't give it a command, don't give it an argument, then it will list the current directory. And this is what I mean by the current working directory is the thing you change with cd is often the one you want to make use of, because that is where many commands will operate by default. There are a bunch of other programs that are useful to know about like this. So for example, there is one called cat. Cat will print out the contents of a file. So if I do cat of stata.config, then when I cat that file, it prints out the contents of that file and dumps them into my terminal. There are other commands like sort. Sort will take its input, or the file that is referred to on its input, and it will print out the lines in sorted order. So if, for example, here I create a data file, and I put in A3BX14, and I type sort data, then it will print those out in sorted order. And in fact, if I do here, let's say I added 31 as well, to prove a point, you'll see that it does lexicographical sorting by default. So 3 is followed by 31, because alphabetically that is the order, even if numerically that might not be correct. For example, if I wanted to add in now, if I wanted to add in 4, and I tried to sort data, then you'll see that I get 3, 31, 4, because they're ordered lexicographically, not numerically. But there are arguments you can pass to sort to change this behavior. Then we have unique. So if I here added 4 a bunch of times, then if I now run unique on data, it will only print out lines that are unique in that file. It only eliminates consecutive lines that are unique though. So if I go into data and I put a 3 in here and type unique data, you'll see that I get 434. So it's not very smart. It doesn't remember every line it's ever seen. It only eliminates duplicates that are consecutive. But you can imagine combining sort and unique to get the functionality you want. Or sort also has a flag, sort-u, which does this for you. It sorts and eliminates duplicates. But we'll show you how to combine commands a little bit later. And then we have head and tail. Head prints the first n lines of a file. The default n here is 10, but you can pass -n and then a numeric argument to say how many lines to include. So head prints from the start of the file, and then we also have tail, which prints from the end of the file. So these allow you to inspect just parts of a file rather than the full file. And then we get into slightly more sophisticated tools. So there, for example, there's a tool called grep. Grep is a file searcher. It doesn't search for files, it searches in files. And it searches for things that match a particular pattern. So for example, if I want to grep for 4, or 3 is maybe a better example, grep for 3 in data. So grep takes 2 arguments, a pattern and a file, or a list of files that you wanted to search in. And it will print out all of the lines that match the pattern that you gave in. So in this case, these lines all match 3, the other lines do not, and therefore do not get printed. Grep is actually much more powerful than it might look like here, because the pattern that you supply is not just a standard text. It is actually what's known as a regular expression. And regular expressions, we're going to touch on these later in the editor lecture, but regular expressions allow you to express quite complicated things. And we'll see an example of that in a little bit that allows you to say, I want to find anything where the first letter is not an A, and the next thing is any numeric digit, and then I want an arbitrary number of characters until a dash. Like those kinds of things. And again, we'll get into the details later, but you can use grep, therefore, to search for fairly sophisticated things inside of potentially large directories that you have. In fact, grep also, in addition to searching files, can search directories. So if I CD, for example,